Sound is produced by vibrating objects. The vibrations cause air molecules to vibrate, which reach the ear and cause the eardrum to vibrate. These vibrations are perceived by us as sound. In a longitudinal wave, the particles of the wave vibrate parallel to the direction of motion of the sound wave. By clicking on Analyze, you will notice that the particles vibrate to and fro along a mean position and do not travel with the wave. One vertical column of particles bumps into its neighboring column and sets it in motion. That in turn bumps into its neighbor, and the vibrations move further and further. By clicking on Compression and Rarefaction, you will notice that in certain regions of the wave, the columns are very close to each other and are called as compressions. There are also regions of the wave where the columns are apart, and those regions are called rarefactions. A column of particles vibrates about the mean position. The displacement between the extreme positions of the particle is known as the lateral displacement. If the lateral displacement of each column is plotted along the y-axis, it displays a wave formation. If you observe only column A carefully, you will notice that as it gets to the extreme position on the right, in the bottom depiction, it gets to the top, and as it gets to the extreme position on the left, in the bottom depiction, it gets to the bottom. The wavelength is the distance between two successive compressions or two successive rarefactions. Take Show Wavelength and take a minute to observe how some pairs of particles move identically on the wave. For example, C and G move together in a compression, and F and J move together in a rarefaction. The distance between C and G, or between F and J, will also represent the wavelength. The frequency is the number of to and fro movements about its mean position in 1 second. Higher frequency will mean that the number of vibrations per second will increase, which in turn means that the number of to and fro motions per second will increase. Amplitude is the distance between the mean position and one of the extremes. High amplitude means that the distance between the mean position and the extremes is larger. When the amplitude is high, the distance between successive compressions and successive rarefactions is high. When sound waves strike a hard medium, they reflect back, just like light reflects off a mirror. The angle of incidence is equal to the angle of reflection. When sound reflects off a surface, an echo is heard. If the reflected sound hits our ear in less than 0.1 second, we cannot distinguish between the sound and the echo. Sound travels at 340 meters per second. This means that if the reflecting surface is less than 17 meters away, it will take less than 0.1 seconds to travel back to our ears. In this case, the echo is not heard. But if the reflecting surface is more than 17 meters away, then it will take more than 0.1 seconds for the sound to travel back, and this is when we would hear the echo. If we can measure the time taken for the echo to reach our ears, we are able to compute the distance from the wall. We know the velocity of sound in air, and we know the time taken. So the distance is velocity times the time taken. But be careful. This gives us the distance traveled by the sound wave to the wall and back. So the distance to the wall is half of that calculated. Bats have very low visibility and have to rely on other senses to find obstructions in their path. A bat sends out sounds which bounce off nearby objects. Amazingly, in some cases, the bats are even able to distinguish food from other obstacles. Ships are able to send ultrasonic waves which bounce back. Knowing the speed of sound in water and measuring the time taken to receive the reflected wave, we are able to estimate the depth of the sea. We have seen longitudinal waves vibrate in the direction parallel to the direction of the wave. The transverse waves vibrate perpendicular to the direction of the wave. The wave is traveling from left to right, whereas the particles are vibrating from top to bottom. All objects which vibrate have a natural frequency, which is the frequency at which they vibrate most easily. Each tuning fork has its own natural frequency. When struck, it vibrates with its natural frequency. The natural frequency of a pendulum depends on the length of the pendulum. The longer the length, the lower the frequency. For the same length of the pendulum, it really does not matter from which point the swing begins. The time taken for one complete oscillation or cycle would be the same. In the animation, the ball below the pendulum is just a reference which displays the reflection of the periodic motion. By plucking a violin string at different parts, it can be made to vibrate at different frequencies. If the string is plucked at the center, the frequency with which it vibrates is called the fundamental frequency and is the lowest frequency of vibration. The fundamental frequency is also referred to as the first. By plucking a violin string at different parts, it can be made to vibrate at different frequencies. If the string is plucked at the center, the frequency with which it vibrates is called the fundamental frequency and is the lowest frequency of vibration. The fundamental frequency is also referred to as the first harmonic. The second harmonic has twice the frequency of the first harmonic. This can be achieved by plucking the string as shown in the animation. The third harmonic has 3 times the frequency of the first harmonic. This can be achieved by plucking the string as shown in the animation. In real life, a spring mass system does not go on vibrating endlessly due to external forces such as air resistance. The amplitude of vibration decreases with each oscillation and eventually dies down. This periodic vibration of decreasing amplitude is called as damping. Free vibrations occur when a force is applied for a brief period, and the body continues to vibrate at its natural frequency. Forced vibrations occur when a force is applied periodically. Here, the body begins to vibrate at the frequency of the applied force. When a tabletop is excited with the same frequency as the tuning fork, the sound produced is much larger as the table area is much wider, and hence more air particles are set into vibration. The frequency of forced vibration can be less than, equal to, or greater than the frequency of natural vibration of the object. When the frequency of forced vibration is equal to the frequency of natural vibration, the amplitude of vibration becomes very large. This is known as resonance. As you increase or decrease the frequency of forced vibration from the natural frequency, the amplitude decreases. When 2 identical tuning forks are placed side by side, and one of them is excited at its natural frequency, the waves at that frequency strike the neighboring tuning fork. It also gets excited at the same frequency and begins to vibrate. This is a phenomena of forced frequency, and in this case, tuning fork B vibrates at the frequency forced by tuning fork A. With each oscillation, pendulum A gives the horizontal string a little pull. Since pendulum A and C are of the same length, the little pull occurs at exactly the same frequency as the natural frequency of C. Eventually, all the energy from pendulum A is transferred to C, and C oscillates with the same amplitude as A's original amplitude. Then, the reverse takes place. Pendulums B and D move with low amplitudes and do not behave as C, since their lengths are different from A, and so is their natural frequency. When the tuning fork vibrates, the air particles above the water are also set into vibration. When the natural frequency of the air column matches with the tuning fork frequency, we hear a sound. Suppose the height of the air column was h at this point in time. As the water level is reduced, we hear sounds at exactly 2h and 3h. As h increases, the frequency of the sound also increases. So at 3h, we hear the highest frequency, and at h, the lowest frequency. the frequency of B is twice that of A. As you can see, twice the number of crests and troughs as that of A. The wavelength of B is half of A, as the distance between successive crests in B is half of that of A. Amplitude is the distance from the mean position to one of the extremes. You can see that the amplitude of B is higher than that of A. The larger the amplitude, the louder the sound. You can see here that a soft note has a lower amplitude than a loud note. Loudness is proportional to the square of the amplitude. This means that if the amplitude of the wave is doubled, the loudness increases by 4 times. Pitch is the characteristic of sound by which a shrill note can be distinguished from a bass note. A woman's voice has a higher pitch than a man's voice. The higher the pitch, the higher the frequency. Therefore, we can say that a woman's voice has a higher frequency than a man's voice. When two waves traveling in opposite directions superimpose, the resultant wave is formed by adding the amplitudes of the individual waves. When different instruments are played, they excite different harmonics simultaneously. For example, let's say that the piano simultaneously produces the first, second and third harmonics. What we hear is a wave that is the combination of all the 3 harmonics, which is called the resultant wave. When a piano is played, the resultant wave may be the combination of the first 3 harmonics. When a clarinet is played, the resultant wave may be a combination of the first, 6th and 7th harmonics. The fundamental frequency played on both is the same, but they sound different. It is the quality or timbre which allows us to differentiate the sounds produced by various musical instruments. Whenever we listen to a sound produced by regular and periodic vibrations, we perceive it as a pleasant sound or music. Noise is produced by irregular vibrations and is very unpleasant to our ears.